Okay, so let's quickly go through the Boltzmann distribution. So we already know that in a gas, particles move with high speed, and as you increase temperature, the speed of the particles will increase. As you decrease temperature, the speed of the particles will decrease. Now, it's important to know that not all the particles in a gas will have the same amount of energy. There is a distribution of energy, and when we talk about temperature affecting the amount of energy, we mean it as an average, because there is a distribution of energies, hence distribution. So there will be no particles with no energy. Okay, that's not possible. And then as we increase the amount of energy, the number of particles with that energy will increase. Okay, up until some point. Okay, so if we look now at this, so this energy here, we've got a lot of particles have got that energy. This energy down here, not many particles have that energy. And then as we increase it further, then the number of particles which have got really, really high energy, that's going to decrease as well. Okay, and then it will tail off. Alright, so we can see that up here, where the energy is really, really high, where the particles are moving really, really fast, there's not going to be very many particles with that much energy. So the important things to note are here, we have no particles with zero energy. Up here, it doesn't touch the x-axis, so it would keep on going. So you increase the energy, and there will always be particles with that amount of energy, but just the number of particles decreases. And you have to remember we're talking on fantastically large scales of quantity here, with numbers with many, many zeros after them, which is why we can keep on going. And number 3 is that the area underneath here, okay, represents the number of particles. Okay, because we're plotting the number of particles with a given energy against energy, so the area under the graph is going to be the total number of particles. Okay, so let's think about 3 different situations where we can use this graph. So situation number 1 is going to be if we change quantity. Okay, so let's imagine we've got a distribution in a certain gas, okay, and then I take half of that gas. All right, so I halve the volume of the gas. If I halve the volume of the gas, I'm going to halve the number of particles. However, I don't do anything to affect the amount of energy the particles have. So, if this value here is, let's call it A, and this value here is A divided by 2, all we're going to do is we're going to have a curve of the same shape, but it's cut in half. Alright, so not sure if these points exactly align, but really the peak should be at the same point, because we haven't done anything. When we changed the quantity, we didn't do anything to affect the speed or the energy of the particles. So when we change the quantity, we just move the curve up and down, and so the area underneath this curve here will be half the area under this curve. Okay, and that's pretty straightforward. So that's situation number 1. Situation number 2 is going to be our change in temperature. So if I have my distribution of energy in my gas, when I change the temperature, I don't change the number of particles. So the area underneath the curve needs to remain the same, but if I'm going to increase temperature, so let's say I'm going to have a second one where T2 is greater than T1. Alright, I'm going to increase the average temperature, which means that this peak is going to shift to higher energy. Okay, but the peak can't be as high, because if the peak was as high, it would mean that the area under the graph would be larger, which means there would be more particles, which isn't possible because I haven't changed the number of particles, I've only changed the temperature. So that would be T2. Okay, so you can see that on average the particles have more energy, and the areas underneath the graphs are the same. Alright, and then our last situation is the effect of a catalyst. So, we all know that a catalyst increases the rate of the chemical reaction by providing an alternative pathway with a lower activation energy, which means that it doesn't affect the number of particles, so it can't affect the area underneath the graph, and it doesn't affect the temperature, so it can't change the amount of energy that the particles have. So in fact, adding a catalyst doesn't change the graph in any way at all. The particles in the gas still have the same amount of energy and there's still the same number of particles. All it does is it changes the activation energy. So if this is the activation energy for a reaction, we can see that in our gas, this number of particles have the activation energy. Okay, so let's say this is without the catalyst, and then if I add a catalyst, I just lower the activation energy. So this can be EA with a catalyst. Alright, and now we can see that the number of particles with the activation energy has increased. I've not added any more particles, I've not changed the energy that the particles have, but because I've decreased the activation energy, the number of particles that exceed that energy has increased. And that is it.